Hello everyone, my name is Tuna and my partner's name is Ali. Together we have designed an experiment named Autogenous welding of plastic bottle lids at home, and via this video recording we are going to present you our lab report for this experiment. Sometimes it is more convenient for one to manufacture piece by piece rather than manufacturing as a whole. This may be because of economical constraints, design considerations, easier opportunity of replacement and maintenance, or just that different mechanical properties are desired in the end product. At this point, welding is a great opportunity. In our modern world, welding is used in many fields such as skyscrapers, ships, cars, and planes. Plastic welding is simply defined as the process of creating molecular bonds between two or more uh, compatible thermoplastics. Consequently, two or more plastic specimens stick together to form a single end product. What is meant by compatible here is that the filler material and the base material should be similar to each other for the bond to be strong. There are a couple of factors affecting the welding strength, such as material choice, welding area, and heating techniques and also cooling techniques. In this experiment, we will mainly focus on the effect of welding area on the welding strength and observe the effect of it. In this experiment, the main goal is performing autogeneous welding operations between plastic bottle lids and observing the change of weld strength with welding area. Welders typically work with metal or thermoplastic and use durable filler material to bind them together. However, in this experiment, we have chosen thermoplastic as base material and we haven't used any filler material. Since we haven't used that filler material, the process is named autogeneous welding. Autogeneous welding is one way of performing fusion welding, which is the process of welding that relies on heating and melting but does not require any external filler material. Welding of thermoplastics is accomplished by localized heat transfer sufficient to produce fusion of the surfaces that are to be joined. When the thermoplastic is heated, its surface softens. The softening leads interface surface to have a viscous and molten state. Then, by application of again sufficient pressure, surfaces of interest make good bonds between each other and so stick together. Then the system is let to cool to ambient temperature. Solidification of material takes place while cooling. The columnar grains begin to form. These grains are long and form parallel to heat flow. If the material were metal, these grains would lie parallel to the interface since the metals are far greater heat conductors compared to air. However, plastic is also a poor heat conductor like air. Therefore, in plastics, grains do not lie parallel to the interface as in metals. After cooling, the resulting product usually has low strength, hardness, and ductility. But with a proper material choice, mechanical properties of the weld can be arranged and increased. It's a remarkable point that since thermal conductivity of plastics is low, application of heat transfer at high rates may cause plastic to burn or char. This situation may further lead to fusion to occur improperly and therefore the desired joint strength may not be achieved. Therefore, one should be careful while conducting this experiment and heat transfer process.
Our experiment is about plastic bottle caps, uh, which is made from propylene, which is one of the easiest thermoplastic materials to use in welding process. The reason behind this is it has a very high tensile strength and very high impact resistance, and it's very rigid as you see. after it's welded, and it is a very convenient idea to use this propylene material or plastic bottle cap as a welding material as well. But the point is, the two materials which are going to be welded must have the quite same mechanical properties with propylene. Otherwise, the welding is not going to happen. The temperatures for propylene welding is about 300 Celsius approximately. And if you are going to use a thermoplastic welder, you have to give it 500 watts and around 120 volts of voltage. And also it has very low water absorption. And let's go to the experiment. We have welded one pair with 100% cross-sectional ratio and the other one with less than 100% and more than 50%. And we have our battle, and with the help of it, we are going to test the strength of the welded area. Now the second one with 100%. So we need two bottles to separate them. So horizontal pull was not enough, so we needed to apply a torsional moment to separate them. So it was much harder than the first one. So it shows us the cross-sectional area of welded polypropylene increased the strength of welded area.
As seen from the tests, a relatively small tensile load was adequate to separate two leads from each other in the half area case. In the full area case, on the other hand, the leads couldn't be separated from each other by application of a tensile load alone, but together with a torsional load. Therefore, it is plausible to deduce that with increasing welding area, the welding strength increases and it gets even more difficult to separate two leads from each other. The reason behind this phenomenon is that with increasing welding area, fusion bonding area also increases. Consequently, relatively more bonds formed by fusion between two leads, which in turn leads particles to stick together stronger and the end product have a greater resistance against loads. Let's have a look at the lead surface after the separation. Bonding marks on the leads and interface surface are remarkable. The full area case specimens have a larger fusion bonding area, whereas half area case specimens have a relatively smaller fusion bonding area as expected. It can be concluded that the experiment is consistent with the theoretical relationship between welding area and welding strength.